Thank you so much. And thank you so much to the organizers for inviting me to give a talk. I'm sorry I couldn't be there in person. So in this talk, kind of following with this theme of complexity, I'm going to talk about a problem which is that of estimating the entropy of states produced by certain types of quantum circuits. So just to start with something a bit pedagogical, I know everyone is familiar with what entropy is, but just to set the convention that I'll be using in the rest of this talk, whenever I refer to classical entropy, I'm referring to the Shannon entropy, and it's always, except for one slide, maybe it's going to be for a distribution on n bit strings, and in the quantum case, analogously, the von Neumann entropy on n qubits. So importantly, the entropy, whether it's classical or quantum, is always going to be between 0 and n. Okay, so the problem we'd like to look at is the following. Suppose you're given the description of some quantum circuit or a classical circuit. We'll look at both problems. And this quantum circuit, it acts on some number of qubits that say we're all initialized as 0. And then it outputs some n qubit quantum state rho. And the goal, as we'll see, will be to estimate the entropy of this state. And I should say that the general width of the circuit is some polynomial in n. So we fix n to be the size of this output state that we care about, and then the general width and size of the circuit can be polynomial in n. So we're imagining like a family of such circuits where n goes to infinity. And in the classical case, you can also consider as input a classical circuit, but there, if you want to have some entropy in your output, your inputs should be random bits. So maybe also 0 bits, but also uniformly random bits. And again, you have some output probability distribution there. And in both cases, the task is given as input the description of this circuit, you should output an entropy estimate for either the quantum state rho or the probability distribution. And specifically, let's say that what we're interested in an additive error entropy estimate to within some fixed small constant, say 0.1. The constant here is arbitrary. It can be whatever you like. But for concreteness, let's just say 0.1. Okay, so in the previous two talks, we heard about, or I should say in Nicole's talk and in Jordan's talk, we heard about computational hardness and complexity. And I'll also be talking about that. So let me just clarify what I mean in my case. So as I said, you're given as input the description of this circuit, and we're imagining that there's some sort of algorithm, in the most general case, a quantum algorithm, that whatever it does with this input, it should somehow output the entropy estimate that I mentioned on the previous slide. So very importantly here, you're allowed to do whatever you want with this description of the circuit that you have. So you don't necessarily need to run the circuit. If you notice some sort of special structure in the circuit that immediately lets you estimate the entropy, you can just do that. But in general, we would like to know what is the fastest such algorithm that works for all possible inputs as a function of n. So by fastest here, you can think of it in terms of runtime or in terms of circuit complexity of this quantum algorithm, like the total number of gates that it would require to solve this problem. And I'll say that it's efficient if it takes polynomial time or it has polynomial circuit complexity, otherwise it's inefficient. And we can immediately see that naive approaches to solving this problem would be inefficient, because what you could imagine doing is, for instance, computing what the output density matrix would be, given the description of the circuit. But of course, that would require exponential time in the number of qubits to do this. What you could also do in the quantum case is you could use the circuit to prepare multiple copies of the state. But as was kind of hinted at in Jordan's talk, in this setting where you're given many copies of some state and you're not using any other information about the state, then again, in general, it's going to take exponential time to estimate the entropy of that state. So it's, in general, kind of as hard as state tomography to solve this problem.
Sorry, let me interrupt you right here. By fastest, do you use one computer or do you take parallel programming processing into account at all?
So, well, I mean, I'm trying to think how best to answer this. Let's just say a fixed algorithm. So, okay, you can run it in parallel on multiple computers, but as long as asymptotically it takes exponential time, like if you run it on, say, in parallel on k computers, maybe you get a speed up of polynomial in k, or maybe even exponential in k, but you should think of this as some constant, so you don't have like an unbounded number of computers that you can use.
Okay,
so
thanks.
Really, yeah. So we're really thinking about the, say, the circuit complexity of this quantum algorithm to solve the problem. Right, so as I said, like the naive approaches that we have seem to all require exponential time. So the question is, can we do better than that? So to answer this question, we need to make a very important distinction here, which is to also consider the depth of this circuit. And intuitively, the depth is important because the deeper your circuit is, the easier it is to scramble information and make this entropy estimation task harder. So it seems like the depth of the circuit is a very important metric that one should consider along with the circuit itself. So first, let's look at the general case where you just have some arbitrary polynomial-size quantum circuit, so it also has polynomial depth. So in this case, based on some plausible conjectures from complexity theory, we think that the problem is hard. So this was shown in the classical case in this paper by Goldreich and Vadan, and in the quantum case by Benaroya, Schwartz, and Tashma. And let me just briefly tell you what they've shown. So in complexity theory, we're usually interested in these two complexity classes. So BPP is the class of problems that we can solve in polynomial time on a classical computer. And BQP is the class of problems that we can solve in polynomial time on a quantum computer. So these kind of correspond to efficient computations, things that we can solve efficiently. So what was shown in these two papers is that for the classical case, this entropy estimation task is complete for some complexity class called SCK. And I won't define what this is, but this is some sort of set of problems that contains a number of problems that are useful in cryptography. So problems that should be hard to solve for both quantum and classical computers. And having a problem being complete for this class means that it's contained in the class and it's also at least as hard as any other problem in the class. So in other words, if you could solve this problem efficiently, you could also solve everything that is in this class efficiently as well. And we believe that's unlikely because of these sort of cryptographic arguments. So that was in the classical case. In the quantum case, the result is analogous for, let's say, the cousin of this class, which is called QSZK, and which we believe is even bigger than SZK itself. So the bottom line is that for polynomial depth circuits, it seems that the problem is hard. And let me just comment a bit about why it seems necessary to make cryptographic or computational assumptions, in contrast to, say, the previous results that we heard of, where there were the results were unconditional. So the difference on the one hand is that, so say with respect to Jordan's talk, is that we're not given copies of the state. We actually know the circuit that produces the state. So we have sort of full information about how the state was produced. And in contrast to Nicole's case, the problem now is that the gates in the circuit need to, because you're given the circuit as an input, the gates in the circuit need to be specified with polynomial precision in this n, which means that the available gate set that you have is a discrete set rather than a continuous set like SU4. So in this regime where you have these sort of limitations, in general, we don't know how to prove unconditional hardness results. We kind of always have to reduce them to other problems that we conjecture are hard. So as we'll see, this problem is also at least as hard as a problem known as detecting collisions for a function, and that's also what we'll use for our results. So what are our results? So we basically looked at the same problem when your circuit depth is much shorter than polynomial. So in particular, when the circuit depth is, say, logarithmic in this number n of qubits. So in this case, we showed that the problem is at least as hard as a problem called learning with errors. And if you're unfamiliar with this problem, this is a problem that's kind of the basis right now for designing cryptographic protocols that would be secure even against quantum algorithms. So it's a problem that for both quantum and classical algorithms, the fastest ones that we know of, they all require exponential time. And people generally believe that this problem will not be solved efficiently. Like there are no efficient algorithms for this problem. So that's one result. And then the other result is, let's also assume now that the circuit has constant depth rather than logarithmic depth. So now the circuit is extremely shallow. So in this case, we need to distinguish between two situations. So one is when we have so-called gates of unbounded fan-out. So in the classical circuit case, this is easy to explain. These are gates that say take two inputs, and then the output is copied many, many times. So for instance, n times. So you can imagine that this might be, say, a Boolean AND gate. So it does the AND of these two input bits, and then it just copies the output n times. So what does unbounded fan-out mean in the quantum case? Because, quantumly, we can't really copy quantum states. So in the quantum case, we mean that we have just our standard gate set of 2-qubit and single-qubit gates, plus some sort of generalized C0 gate. So a gate that has one target and multiple, one control and multiple target qubits that it can act on. And the other situation is the more familiar case of bounded fan-out gates, where we just have, say, two outputs for each gate in the circuit at most. So in the case of unbounded fan-out and constant depth, we can show that the problem is still as hard as learning with errors. And in the bounded fan-out case, the situation is kind of strange. So the classical case is easy. There is an efficient algorithm for estimating entropy. But the quantum case doesn't seem to be easy, but we also don't know if it's hard. So I should correct myself if you saw a previous version of me giving this talk where I said that the quantum case is also hard. So it turns out that there was a bug in that proof, and we don't actually know if the quantum case is hard, but we also don't know if it's easy. So it's still an open problem to determine this. I'll comment more about this later on. Okay, so let me tell you at a high level how we would show hardness for log depth circuits. And you can also apply this intuition for like anything larger than log depth. So suppose that we have a function that is 1-to-1. So say from n-bit strings to n-bit strings. So it's an injective function. In this case, it's also a bijection. And we have another function g, which is a 2-to-1 function. So this one maps pairs of inputs to one output. It kind of collides inputs. And these pairs of inputs that map to the same output are called collisions of the function. So let's imagine what happens when we evaluate either of these two functions with a uniform input. So we can see that if your function is injective, if it's 1-to-1, then f of x is just uniform on this entire output domain. And in the other case, it's uniform on half of the output domain. So if you look at the entropies of these two random variables, for the 1-to-1 case, it's going to be n. It's the maximum entropy that you can get. And in the other case, it's n-1 because you're only using half of the output space. So it's because you have these collisions in your function. So of course, if you have circuits that, like classical circuits that implement these functions, you can also come up with quantum circuits that generate these states where I'm taking the equal superposition over all inputs. And if you trace out either of these two registers of the state, the remaining register will have entropy n in the 1-to-1 case and entropy n-1 in the other case. And so the general idea will be that if you can estimate entropy to within an additive error of, say, 0.1, then you'd be able to tell, if I give you such a function and you implement this circuit, whether you were given the 1-to-1 function or the 2-to-1 function. So let me just make this idea a bit more concrete. So now we're considering this related problem where I give you as input a circuit and I promise you that the circuit is creating such a state. And the problem here is to determine whether this function h is a 1-to-1 function or a 2-to-1 function, promise that it's only one of these two functions. So as I said, if we could estimate entropy, then we could answer this question. So if there were an efficient algorithm for estimating entropy, then you could also efficiently solve this problem by just seeing if the entropy is closer to n or n-1. So then what we'd like to do is to come up with a way to implement these functions so that distinguishing whether we have a 1-to-1 or a 2-to-1 function is hard. So that's what we'll do now. So one function is this f function here. They're both very similar. And the inputs are, so this b input is a single bit, and then everything with an arrow on top is a vector. All the vectors are with components modulo q, so the integer is mod q. And this A is a matrix mod q, an m by n matrix. And you should think of m as being much larger than n, so it's like a very tall matrix. So what's happening in these functions is we're computing a times x plus this vector e, and then condition on the value of b, so whether b is 0 or 1, you may or may not add another vector here. So in this case, if b is equal to 1, you add this u vector. Otherwise, this is just 0, so it disappears. And for this other function, if b is equal to 1, you add this as plus e prime vector, and otherwise you don't. So the only difference between the two functions is whether you're adding this u vector or this as plus e prime vector. So now the idea is to think of this u vector as being a uniformly random vector of components modulo q, whereas this other vector here we can see as some sort of vector that is of the form as plus e prime. And you should think of both this e vector and this e prime, I'll call them error vectors, as having very small norm. So in particular, the norms of these two vectors should be much smaller than the norm of this u vector. So if this is the case, it means that this as plus e vector is some vector that is very close to the image of the matrix A. And whereas the uniform vector in general will not be close to the image of the matrix. So then let's see what happens with the outputs of these two functions if we look at like what the possible b values are. So for the f function, if b is equal to 0, then we just output ax plus e. So this is something that is close to the image of A. Now, if b is equal to 1, we output ax plus e plus this uniform vector, which in general will not be close to the image of A. However, for this g function, when b is equal to 0, it's the same as the f1, so it just outputs ax plus e. But when b is equal to 1, it outputs ax plus e plus a vector that is also close to the image of A. And so the overall output will be close to the image of A. And so what this means is that this function, this f function, if you assume that these inputs are random, and constraining that this e vector should be a low norm vector, so there you only randomize over vectors of very low norm, this vector with high probability, this function with high probability will be injective, whereas this other function is very likely to be 2-to-1. So there are very likely to be collisions because your outputs are always close to the image of the matrix A. And the learning with errors problem is exactly the problem of distinguishing between being given a uniform vector or a vector that is close to the image of some matrix A. And you're also given the matrix A as input. So we can see that in order to implement these functions, you only need the matrix A and the uniform vector U as parameters to specify. So if you could determine which one of these is the 1-to-1 function and which one is the 2-to-1 function, you could also distinguish between these two cases, and that boils down to solving this learning with errors problem. Okay, so that's the idea. Like that's how you can kind of reduce the hardness of distinguishing between these two functions to the hardness of entropy estimation. And what's important to note here is that these functions only involve linear algebraic operations, and these are very easy to parallelize, so you can do them in parallel. And this means that the overall circuits you get will be logarithmic depth circuits. So you can show that there are in fact logarithmic depth circuits that can implement these functions. And so your overall circuits will have logarithmic depth. Okay, so this kind of shows the hardness of log depth estimation of entropy for log depth circuits. So what about the constant depth case? So I won't go into details on this, but there we used another notion from cryptography called randomized encodings. And this will also give you, for constant depth circuits with these unbounded fan-out gates, that you can also have a reduction to this learning with errors problem. Okay, So I should also comment here that you kind of saw that the function is 1-to-1 or 2-to-1. This kind of gives us 1 bit of entropy difference. It's very easy to generalize this construction by considering 2^k⁴ functions instead of 2-to-1 functions. So now you're colliding 2^k inputs instead of just 2 of them. And in this case, you would get k bits of difference in entropy. And so you can also construct these functions from learning with errors. And if you take this k to be, say, some linear function in n, then you can also get that entropy ratio is hard. So you can engineer states that have some sort of constant entropy ratio. And again, distinguishing between these two should also be hard based on learning with errors. So in this case, I just took as an example n and n/10 for entropy. Okay, so maybe I should just pause for a second to ask if there are questions before talking about the constant depth case and bounded fan out. Okay, so if not, so what happens now if we look at the constant depth case and we have bounded fan out in our circuit and also bounded fan in? So let's look at the classical case first. So now we have a classical circuit, assume that the inputs are just uniformly random bits, and we have some output here, some output bits, n of them. So one thing that is very natural to do is to say, let's try to use the entropy chain rule to compute what the entropy of this output is. So you can write the entropy of the output as the sum of these conditional entropies where I is from 1 up to n. And it's important to note here that whenever xi and xj are independent random variables, then this conditional entropy of xi conditional on xj is just equal to the entropy of xi. Okay, so let's focus on one specific xi. So Nicole introduced this concept of the light cone in the circuit. So to kind of see what we'll try to see is which other output bits is or can xi be correlated with. And to determine this, we need to first go back through the circuit and see which inputs xi can depend on. And this is given by the backwards light cone of xi. And this, of course, will be bounded by the fan-in of each of these gates to the power the depth of the circuit. And because the fan-in is constant, this is a constant size set. So it only depends on a constant number of input bits. Then what we can do is we can take the forward light cone of all of these inputs in this set B. And this will give us all of the outputs that xi could in principle be correlated with, as well as xi itself. So you should think of these as all possible output bits that could in principle share a common past with xi. And this again will be of constant size because the fan out is of constant, it's bounded, it's constant as well. So now we notice the fact that if you have some variable that is outside of this set, it's going to be independent of xi. And so this means that when we look at this chain rule entropy, at this formula for, at the chain rule entropy formula, when we condition here on all of these variables, really we are only interested in the variables that xi could be correlated with, because everything else, if it's uncorrelated, it's not going to affect the entropy. So that means taking this set of the forward light cone of the backwards light cone of xi and subtracting xi itself from it. And we can just express this as this entropy minus this entropy using the formula for conditional entropy. And importantly, as I mentioned, these sets are of constant size. And that means that you can compute this entropy in constant time by just looping over all possible values of the variables that you have in this set. And so that means that this entire sum can be computed in linear time. So you have n terms in the sum, each term can be computed in constant time. So then the overall sum can be computed in linear time. And therefore we have an efficient algorithm for computing this entropy. So now you might ask, why doesn't this argument work in the quantum case as well? Because of course the chain rule also applies. So what's going on in the quantum case? So to explain why it doesn't work in the quantum case, it's useful to consider an example. So suppose our circuit, we start with a bunch of qubits that are initialized as 0 and a bunch that are initialized as plus, so equal superposition of 0 and 1. Of course, we can get this with just one layer of Hadamard gates on a bunch of 0 qubits. And then what we do with these plus qubits, so you kind of take them 2 by 2, and you perform a CNOT gate in these blue qubits. So this is kind of like computing the coherent parity of pairs of qubits in these blue qubits. And then you do the same with the green qubits. So the green qubits will store the parities of these neighboring qubits and so on up to the end of the circuit. So all of this can be done in constant depth, like you have a constant number of layers of gates that you can apply. And then suppose that we measure these parity qubits, so the blue and the green qubits. Well, it's not too difficult to show that the state on the remaining red qubits is going to collapse to an equal superposition of 2 strings, Z and the complement of Z, such that these strings satisfy whatever parities we obtained as a result of the first measurement. So when we measured these blue and green qubits, we got these parity values AIs, and these 2 Z strings need to satisfy these parity conditions. And there are only 2 such strings that satisfy these conditions. So now suppose we also measure the red qubits. So we measure this state, which is like a G8Z state, but it has the bits being flipped. So this X string that we get as a result of this measurement is one of these 2 strings, either Z or Z bar. And now suppose you ask, what is the probability that, say, X1, after you do this measurement, is equal to 1, condition on knowing all of the parity bits? Well, because it's equally likely that you're either Z or Z bar, the probability that this is 1 or 0 is going to be a half if all you know is the parity bits. But if you know 1 extra bit, so if you know also the result of one of these other X values, then you also know whether you're in Z or Z bar. And now this probability is determined. It's either 0 or 1, like you know exactly what this value is. And the same thing happens to the entropy. So in one case, the entropy is its maximal value, 1. And in the other case, it's 0, because you know exactly what this value is. So what this means is that in the quantum case, unlike the classical case, we can't reduce these conditional dependencies to constant size, because you might have dependencies on things that are outside of the light cone that could affect your entropy. And this is a result of the non-local correlations that can happen in the quantum case when you entangle states in this way. So this only shows that the previous argument doesn't hold for the quantum case. It doesn't actually prove hardness of estimating entropy in the quantum case. And as I said, we had an argument for that, but it turned out to be flawed. And it's open if we could actually show that it's hard, or maybe there is some clever, efficient algorithm that could estimate entropy in this case. Okay, so to kind of end things, I'd also like to talk about how these results could potentially connect to ADS-CFT. And I should say that coming from a computer science background, I know very little about ADS-CFT. So I'm kind of hoping that maybe with discussions with some of you, we could maybe formalize this argument. And apologies in advance if this is not too precise or too rigorous. Okay, so ADS-CFT, as I'm sure people are familiar with, it's this correspondence between some sort of bulk theory in an anti-de Sitter space and a boundary theory that is a conformal field theory. And here, like psi ADS is some sort of quantum state in the interior. HADS is a Hamiltonian that could describe the evolution of that state in the interior. And analogously, we have states, the state and the Hamiltonian on the boundary. And it's believed that there's some sort of dictionary that can relate these two quantities. And one question we can ask is this dictionary efficient? So in the sense that if you want to say map from a CFT state to an ADS state, is there some sort of efficient unitary, for instance, that can do this mapping? Analogously, is there some sort of efficient procedure that can map between evolutions or observables or any other quantities that we might be interested in? So there has been some recent evidence that the dictionary might not be efficient in general, so that you might construct situations where the mapping between the two is computationally intractable. And that's kind of what we're also hinting at with this hardness of entropy estimation. So the idea that kind of leads to this is if you consider, for instance, a state that is supported on this boundary of some size A, then famously we know from the Ryutakeyanagi formula that the entropy of this state should be to leading order the area of some sort of minimal surface that encloses it in the bulk. And so the idea now is that we've kind of seen that estimating entropy seems to be a hard task. But on the other hand, if you're some sort of observer in the bulk and the entropy of this boundary state is related to some sort of geometry of the bulk, then you would think that bulk observers would be able to distinguish between different geometries in the bulk. So between, say, having high curvature and low curvature, for instance. And so then the question is, could this somehow allow us to efficiently estimate the entropy of states? So the way I was sort of thinking about it is in the following type of, say, thought experiment. So suppose we have two possible situations. You have some sort of bulk observer and this Ryuta-Kyanagi surface. In one case, let's say it's very large, and in the other case, it's small. So maybe you have high curvature versus low curvature. And in each of these two cases, this corresponds to having some sort of CFT state that maybe was constructed using one of the functions that I mentioned previously. So these functions that would lead to differences in, like, noticeable differences in entropy between the two states when you trace out part of the system. So again, you know, if you want to take the entropy ratio version, you could say that maybe this state has n bits of entropy, this one has n over 10. And so this also relates to the areas of these surfaces in the same way. So what we'd like to do now is suppose that we actually prepare these states, or one of these states, on a quantum computer. We'd like to kind of simulate the evolution of the bulk observer so that it measures the curvature inside its spacetime and is able to somehow tell us whether it's high curvature or low curvature. So which one of these two situations is that observer in? So to kind of do this efficiently, you need to assume that these states could be produced efficiently. And in general, I'm not sure exactly how one would do that, but we saw that at least we can generate states of very low depth for which there is a noticeable entropy difference. And we also want these states to have a property that I'll just call bulk similar. And by this, I mean that in both cases, there's a well-defined observer inside the bulk that we can time evolve to perform a measurement of the geometry of that bulk. So really, I only want the states in the interior to differ only by the geometry, say close to the boundary, but not by how the observers are in the interior. Okay, so let's assume that we can prepare these states. We prepare them on a quantum computer, for instance. So then we would use the dictionary to determine what the Hamiltonian evolution would have to be for these states to correspond to an evolution of this bulk observer measuring the curvature, say, of its spacetime. So that's something like, say, it sends light signals maybe to the boundary. We know that these should return to us in a finite amount of time. And then from these light signals, maybe we can reconstruct information about what the curvature looks like. So we're using the dictionary here because, you know, if we have an observer in the bulk, we might know what that evolution should look like in the bulk for it to perform this measurement. And we need to translate that into an evolution on these CFT states that we prepared. So then we just evolve these states. And the time of this evolution should presumably be polynomial in the ADS radius and the size of this surface, which should be polynomial in, say, the entropy or in n. And so then what we'd like to do is, if the observer sees a small curvature, let's imagine that it destroys the universe. So maybe it creates a black hole or something. And in the other case, it does nothing. So the idea is to, in the two situations, to create two radically different states in the bulk that we could then easily distinguish if we use the dictionary. So again, in one situation, maybe it creates some sort of black hole inside the interior, and the other it does nothing. So using the dictionary, we might then be able to map back to states that we could efficiently distinguish on the quantum computer. So obviously there are a lot of questionable steps in this procedure, but assuming everything works out, it kind of implies that there would be an efficient quantum algorithm for distinguishing between these two entropy cases, unless this dictionary is inefficient, or, you know, unless some of the other assumptions that we made don't hold. But at least to me, it seems like the dictionary is really the essence of this experiment. So one last comment that I'd like to make about this is you might be wondering, what does this have to do with low depth? So this was kind of the reason we started thinking about this is because of this idea that these CFT states are associated to mirror tensor networks, which have, say, logarithmic depth, so it's some sort of log depth tree. And this kind of motivated the question of, if you have states that were produced by log depth circuits, is it hard or easy to estimate their entropy? So obviously you'd need to constrain these states to the ones that you actually could have in a conformal field theory, and not these sort of contrived states that I was considering. But presumably, if there is a way to relate the two, then the result would be applicable to ADS-CFT as well. Okay, so to wrap up, I kind of talked about these results for the hardness of entropy estimation for shallow circuits, and we saw that the problem is in general hard. It seems to be easy only for constant depth classical circuits with bounded fan out. Quantumly, we don't know what the hardness is, and we used ideas for cryptography to arrive at these. And as I said, I think there might be some interesting connections to ADS-CFT, but I'd be very curious to know what people think about this. So thank you. So I'm happy to take questions.
Yeah, so I have a question. So do you think that this constant depth case is actually going to be quantumly hard? You have some intuition that maybe the prior proof you had could be fixed, or is it you think it's actually easy?
Right. So we have a different proof now that's based on a different problem called learning parities with noise, which is kind of related to LWE, but there's less evidence of it being hard. We still think it's a hard problem even for quantum computers, but there's less evidence for this. Basing it on learning with errors, I'm not sure if that's possible, but because we think we could base it on this LPN problem, my intuition is that it's still a hard problem.
Thanks. Any further questions? If not, let's thank the speaker again. Thanks so much.